Hello friends, welcome to Engineering Funda family. In this video, I'll explain mathematics of Smith chart. If you are communication engineer and if you want to design RF circuits or antennas, then analysis of RF circuits and antenna can be done using Smith chart. In this video, I'll explain structure of Smith chart. Here I'll be deriving equations of structure of Smith chart. If you observe Smith chart, then in that we have two categories of circles. If you observe these circles, then this category of circles are real circles. And if you observe second category of circle, then that is happening like this, you can observe. So this category of circles are imaginary circles. In this video, I'll derive equations of this circle, and based on those equations, I'll explain you exact meaning of those circles. To derive equations of those circles, you need to consider reflection coefficient. The reflection coefficient that I have already derived in my earlier videos of this video lecture series of microwave engineering. Reflection coefficient is ZL minus Z0 divided by ZL plus Z0, where ZL is load impedance and Z0 is characteristic impedance. So reflection coefficient is ZL minus Z0 divided by ZL plus Z0. In Smith chart, we will be plotting impedance as per normalized impedance. To get normalized impedance, I'll be dividing numerator and denominator by Z0. So in numerator, we will be having ZL by Z0 minus 1, and in denominator, we will be having ZL by Z0 plus 1. See, in Smith chart, we will be plotting impedance, and those impedance will be normalized impedance. To get normalized value, you will have to divide characteristic impedance, right? So here, what I'll be doing is, I'll be considering normalized impedance, normalized load impedance ZL, that is actual value of load impedance divided by characteristic impedance, right? So if you substitute that over here, then reflection coefficient equation that will get modified to normalized load impedance minus 1 divided by normalized load impedance plus 1. Now with this load impedance, there are few basics that you need to understand. See, with load impedance, we have two components. Load impedance, that is having real component, that is resistive element, and imaginary component, that is reactive element. So here, see this real component, that is resistive element, and this imaginary component, that is reactive element. If you talk about reactive element, then this reactive element can be positive or negative. If you have positive value of X, then this reactive element that will be inductive. And if you have negative value of X, in that case, this reactive element that will be capacitive. See, here we are talking about impedance. So that impedance with reactive element that could be inductive or capacitive, that is depending on polarity. If you observe value of inductive impedance, then that is J omega L. And if you talk about capacitive impedance, so that is 1 divided by J omega C. If you take this J on numerator, then that will be minus J divided by omega C. So you can clearly observe over here, this capacitive impedance that is negative over here, and this inductive impedance that is positive over here, right? Now what I'll do is, I'll substitute these resistive and reactive elements in this equation to have further modification of this reflection coefficient. So reflection coefficient will be R plus Jx minus 1 divided by R plus Jx plus 1, right? Now with this equation, we need to separate real and imaginary component. So what I'll be doing is, I'll be taking real elements on one side. So R minus 1 plus Jx, that is there with us. And in denominator, we have R plus 1 plus Jx, right? Now we need to separate real and imaginary component over here with this reflection coefficient, right? To have separation of real and imaginary component, we need to multiply and divide complex conjugate of denominator. So if you observe denominator over here, that is r plus 1 plus jx. Complex conjugate will be r plus 1 minus jx. So that is what I'll be multiplying and dividing over here for a separation of real and imaginary components. Now, to separate real and imaginary component, let me write denominator first. Here denominator is how much? R plus 1 square, R plus 1 square minus j square x square minus j square x square. J square is minus 1. So here this minus minus, that is getting plus over here, right? Now in numerator, we need to separate real and imaginary component. So here if you observe real component, so that is r minus 1 into r plus 1. So r minus 1 into r plus 1 is r square minus 1 square, right? And another real component will be jx into minus jx, that is minus j square x square. Minus j square x square is plus x square. So that much real components are there. Now if you talk about imaginary component, then in imaginary component, this jx, that is getting multiplied with r plus 1. So jx into r plus 1, that is xr plus x. And this minus jx, that is getting multiplied with r minus 1. So here minus xr and minus minus plus x is there, right? Now if you observe here, see this xr and this xr, that is getting cancelled, right? So now I'll be writing this reflection coefficient as per separate real component and imaginary component. So here we have real component, that is r square plus x square minus 1, right? Divided by r plus 1 whole square plus x square. This much real component is there. And here we have imaginary component. So that is the x plus x, 2x is there in numerator. And in denominator we have r plus 1 square plus x square. So that is how we can have real and imaginary component. Now here we need to understand real and imaginary component. So here one should know, say this real component, that we are saying that is A over here. And this imaginary component, that we are saying that is B over here, right? See, based on real and imaginary component, we can have equations of circles. The reason is, see, here in this Smith chart, we have real circles like this. And we have imaginary circles like this. So we need to have equations of real components and imaginary components, right? So here, to get equations of real components and imaginary component, here we have real value which is there with A. This belongs to real value. And here we have imaginary value that belongs to B, right? So what I'll do is I'll be considering this A and B separately. So here we have A, that is this. Let us say this is equation number 1. And we have value of B, that is imaginary value, that is this. Let us say this is equation number 2. Now if you observe here in equation 1 and in equation 2, we have two unknowns. Unknowns are R and X. R is real component of impedance and X is imaginary components of impedance, right? And everything is normalized over here, remember this. Here, see, we have two equations. So, but obviously from two equations, we can have two solutions. I'll be writing solutions directly over here. The reason is we are deal with to understand how equations are there, right? So what I'll do is I'll be considering solution of R and X over here. So if you solve equation 1 and 2, we will be having x square, that is unknown quantity. Here instead of x, I am writing x square, that is A into r plus 1 square minus r square plus 1. And in denominator, we have 1 minus A. Let us say this is equation number 3, and real value r, that will be r is equals to square root of bx into 2 minus bx minus b divided by b. Let us say this is equation number 4. Now using these equations 1, 2 and 3, 4, we can have equations of circles. If you substitute equation 3 into 2, then you will be having equation of real circles. And if you substitute equation 4 into equation 1, then you will be having equations of imaginary circles. Let me write that first. After substituting 3 into 2, you will be getting equation of real circles, that is a minus r divided by r plus 1 whole square plus b square, that is equals to 1 divided by r plus 1 whole square. If you observe this equation, then that is equation of circle. And here with this equation of circle, what is center? The center C1, that is a coordinate, that is r divided by r plus 1, and coordinate of b, that is 0 over here. And what is the radius over here? Radius r1, that is 1 divided by r plus 1. And this is what equation of real circles, right? So this is what equation of real circles. And if you want imaginary circles equation, then you will have to substitute equation 4 in equation 1. After substitution of 4 into 1, we will be having equation of imaginary circles, that is a minus 1 square plus b minus 1 by x whole square is equals to 1 by x whole square. If you carefully observe this equation, then with this equation, we have center C2. That center of circle will be how much? That will be having a coordinate, that is 1, and that will be having b coordinate, that is 1 by x. And radius of this circle, that is 1 by x. And these are the circles, those are imaginary circles, right? These are the circles, those are imaginary circles. So we have these two equations, that is representing circles, and those circles are plotted inside Smith chart. Let me explain you how. If you talk about these circles, then these circles are real circles. And these real circles, that is having equation, that is a minus r by r plus 1 whole square plus b square, that is equals to 1 divided by r plus 1 whole square, and that is having center r divided by r plus 1, comma 0, and radius 1 divided by r plus 1. So that is how these real circles are there. And if you observe these circles, so those are imaginary circles, and that is been defined by this equation, right? That is having center 1 comma 1 by x, and its radius is 1 divided by x. So if you observe these circles, then these are the circles, right? These are the circles, those are imaginary circles. These circles are there with this Smith chart. Now always remember this, here in this Smith chart, we are plotting impedance, and that is normalized impedance, right? And that normalized impedance, that is having resistive element, that is real component, and that is having reactive element, that is imaginary component, that is x. And based on those elements, we can understand reflection coefficient, we can understand VSWR, we can understand the value of impedance with respect to length of transmission line, as well as we can analyze radiation mechanism. To understand all those basics, let me explain you few cases over here. So first case, that is based on value of r and x, that is infinite. If you have value of r and x that is infinite, then what will be circles which is there with real and imaginary component? The real circles, that is having center C1, that is r divided by r plus 1 comma 0. Now if you have r and x, those are infinite. So here r is infinite. So here what I'll be doing is I'll be taking r common from numerator and denominator. So I'll be having 1 divided by 1 plus 1 by r comma 0. Now if you place r is equals to infinite, then 1 divided by 1 plus 0 will be there. So this circle C1, that is 1 comma 0, right? And if you talk about radius r1, then what will be that radius? Radius r1, that is 1 divided by r plus 1. So 1 divided by infinite, radius r1 is 1 divided by r plus 1, where r is infinite. So 1 by infinite is 0. So here real circles, that is having center, that is 1 comma 0, and radius, that is 0, right? And if you talk about x is infinite, then x belongs to imaginary circles, right? X belongs to imaginary circles. And with imaginary circles, center is C2. And what is that center? Center C2, that is 1 comma 1 by x and radius 1 by x, right? So center C2, that is having center, that is 1 comma 1 by x, and here 1 by x, x is infinite over here with this case, right? So 1 by x, that is resulting into 0. So center will be 1 comma 0, right? And if you talk about radius of this imaginary circle R2, that is 1 by x, where x is infinite. So 1 by infinite is 0. So if you observe, if you have r and x infinite, at that time, the center is 1 comma 0 and radius of real and imaginary circle, that is 0. So what it means? It means all the circles are getting converged at a point, and that point is 1 comma 0 point. Now what is the location of that point? If you observe, see with this Smith chart, then with this Smith chart, here the point which we have is 1 comma 0. Here the point which we have is 1 comma 0. If you talk about this center, then this point is having value 0 comma 0. And this is what we are talking with respect to A and B. Remember this. This is what we are talking with respect to A and B. It is not about R and X. This 0 comma 0 and 1 comma 0, that is there with A and B. What is A and B? A and B, that is real and imaginary value of reflection coefficient, right? So here, see, we have these points, and with respect to these points only, these circles are plotted. So here, if you have R and X, that is infinite, at that time, this real and imaginary circles, that is getting converged at this point. Why it is getting converged at this point? The reason is radius is 0 over here, right? Let me note down that point. So all the circles, that is getting converged at this point, right? Now I'll explain you second case, in which what if we have r is equals to 0. See, if r is equals to 0 is there, in that case we are little bit to talk about real circles. Real circles means these circles, right? And with real circles, center C1, that is how much? Center C1 is r divided by r plus 1 comma 0. Now here, as if this r value is 0, if this r value is 0, in that case this center will be how much? 0 comma 0. This center will be 0 comma 0. And what will be radius r1? Radius r1, that is 1 divided by r plus 1, right? I have derived this, you see. Radius is 1 divided by r plus 1, right, with real circles. So here if you substitute r is equals to 0 in this, then 1 divided by 0 plus 1, that is 1. So what it means? If you have r is equals to 0, in that case we have center, that is 0 comma 0. And what is that center? 0 comma 0, that is this center, 0 comma 0. And it is having radius, that is equals to 1. If you have radius that is equals to 1 with this center, then what is that circle? That is the boundary of this Smith chart. So this circle, that is a boundary of Smith chart that is happening at resistive element is 0. So as and when you have impedance which is having resistive element 0, then that belongs to this boundary of Smith chart, right? And on this boundary of Smith chart, we only have impedance that belongs to reactive impedance, right? Now I'll explain you one more case study that is quite interesting, that belongs to what if x is equals to 0. X belongs to imaginary component, right? Means if you have load that is inductive or capacitive, if it is 0, then what will happen? Then we need to see these imaginary circles, and for imaginary circles I have explained you equation of circle. If you talk about imaginary circle, then center is C2, and that center is how much? 1 comma 1 by x, where if x is equals to 0, then this center will be how much? That center will be 1 comma infinite, right? That center will be 1 comma infinite. And if you talk about radius R2, then that is 1 by x over here with imaginary circles, and 1 by 0, that is infinite, means radius is infinite. Then what is the meaning of this? See, if you have center that is 1 comma infinite, and as if radius is infinite, then that is not circle, that is a equation of line. Let me explain you how. See, that line will be this, which is bisecting this Smith chart into two halves, right? So here, see, you are talking about line. Actually, the line which is having infinite radius, that is actually a circle, but practically it is a line only, right? If you have infinite radius, then practically that circle will be line. Where this line of this Smith chart that is having radius R2, that is infinite, and it is having center C2, that is 1 comma infinite. So here, when you talk about impedance which is having reactive element that is equals to 0, at that time that point belongs to this line, right? That point belongs to this line. And here one more thing that you need to understand. See, here these circles are imaginary circles. So imaginary component that can be having two values, positive or negative. If x is having positive values, then see, these are the circles that is having positive values, right? These are the circles that is having positive values. And if you talk about x value that is negative, then see, these are the circles that is having negative value of x. And if you have x is equals to 0, then we have line which is bisecting this Smith chart like this, which is having radius infinite, and center C2 that is having value 1 comma infinite, right? And one should know, see here this point that is having coordinate 1 comma 0, and this point that is having coordinate 0 comma 0, and these coordinates are there for A and B, that belongs to reflection coefficient, right? Now one more case is there that belongs to what if we have R which is negative. So one should know, see this Smith chart that plots impedance as per real and imaginary component. So here we are talking about impedance, right? If you talk about X, then you talk about R plus JX, where here this R explains resistive component and this X explains reactive components, right? So R is always positive for resistive element. It cannot be negative. While these reactive elements that can be negative or positive, that depends on inductive or capacitive load. But in research you may have found there are few materials like metamaterials, so that is having negative resistance, right? But that negative resistance cannot be plotted over here in this Smith chart. So as and when you have R that is negative, at that time you cannot do anything with Smith chart. You can say here there will be oscillations inside drawing of Smith chart. That's why we cannot do any research which belongs to R is equals to negative value, right? So as and when you have R which is negative, at that time it suggests oscillation. At that time, analysis cannot be done with the use of Smith chart. So that is how basic parameters are there. Now in future coming videos, I'll be solving few interesting examples using Smith chart, which will improve your understanding furthermore. Still, if anything that I would like to share, just note it down in comment section. I'll be happy to help you. Thank you so much for watching this video.